Hi everyone. In this video, I would like to give a small presentation on representing knowledge in an uncertain domain. Contents covered in this video: introduction, challenges, probabilistic models, fuzzy logic for handling uncertainty, artificial intelligence approaches for uncertain knowledge representation, evaluation and validation, applications and conclusion. Introduction to representing knowledge in an uncertain domain. Uncertain domain refers to areas where there is incomplete or ambiguous information. Advanced AI systems need to be able to handle uncertainty in order to make accurate decisions. Representing knowledge in uncertain domains is essential for AI systems to effectively operate in real-world scenarios. The challenges in representing knowledge in uncertain domains. Uncertainty arises due to limited data, conflicting information, or changing circumstances. Representing uncertainty requires capturing probabilistic relationships between variables. Balancing the trade-off between accuracy and efficiency is a major challenge in uncertain domains. Representing uncertain knowledge points, symbolic and natural uncertainty, the closed world assumption, predicate completion, taxonomic hierarchies, abduction, truth maintenance, base rule, certainty factors, and the fuzzy sets. Probabilistic models for representing uncertain knowledge. Bayesian knowledge. Bayesians are graphical models that are directed acyclic graphs to represent probabilistic relationships among a set of random variables. They are widely used for uncertain knowledge representation in various fields, such as healthcare, finance, and natural language processing. Bayesians allow modeling dependencies between variables and make probabilistic inferences based on observed evidence. Markov decision. Markov networks are unidirectional graphical models that represent probabilistic relationships among variables. They are used in situations where Bayesians might not be sufficient, especially for modeling complex interactions between variables with symmetric dependencies. Hidden Markov model. HMMs are statistical models used to model sequences of observable variables whose underlying states are hidden or not directly observable. They are widely applied in speech recognition, bioinformatics, and natural language processing (NLP) for modeling sequential data with uncertain data transitions. Fuzzy logic for handling uncertainty. Fuzzy logic allows for the representation of impulsive of or vague information. Fuzzy sets and membership functions are also used to assign degrees of membership to elements. Fuzzy rules and fuzzy inference engine enable reasoning and decision making in uncertain domains. Fuzzy logic helps in handling impulsive data. Traditional logic relies on crisp binary rules. Binary rules are which is either true or false, whereas fuzzy logic allows for degrees of truth. Fuzzy logic measures depends upon the degree of the truth. This is particularly useful when dealing with data that not clear-cut and contains ambiguity or imprecision. Linguistic variables and fuzzy sets. Fuzzy logic uses linguistic variables and fuzzy sets to represent vague concepts linguistically. For instance, terms like hot, cold, fast, or slow can be represented in fuzzy logic to capture their inherent uncertainty and subjectivity. Third one is membership functions. Fuzzy logic employs membership functions to assign degrees of relationship membership to elements in a set. Instead of strict categorization, membership functions enable a gradual transition between being a member or not, allowing for more nuanced representation of uncertainty. Artificial intelligence approaches for uncertain knowledge representation. The first one is probabilistic reasoning. Probabilistic graphical models such as Bayesian networks, Markov networks, and hidden Markov models are extensively used to represent uncertain knowledge. They model relationships between variables probabilistically, allowing for reasoning under uncertainty. The second one is fuzzy logic. Fuzzy logic is employed to represent and reason with uncertain or impulsive information. It enables the representation of uncertainty through linguistic variables and fuzzy sets, allowing for approximate reasoning. Ontologies with uncertainty. Ontologies augmented with probabilistic extensions of fuzzy logic can handle uncertain knowledge representation. These ontologies allow for the explicit representation of uncertainty in relationships between entities in a domain. Bayesian model in artificial intelligence planning. Bayesian networks are integrated into artificial intelligence planning systems to model and reason about uncertain states, actions, and outcomes. This incorporation of uncertainty represents in helps in decision making under partial observability. Evaluation and validation of uncertain knowledge representations. Metrics such as accuracy, precision, recall, and FI score can be used to evaluate the performance of uncertain knowledge representations. The second one is cross-validation techniques, which can assess the generalizability of the models. Real-world testing and user feedback are crucial for validating the effectiveness of uncertain knowledge representations. Coming to the applications of uncertain knowledge representation in advanced AI. Autonomous driving systems rely on uncertain knowledge representations to navigate complex environments. Healthcare systems use uncertain knowledge representations to assist in diagnosis and treatment decisions. Finally, financial prediction models leverage uncertain knowledge representations to make informed investment choices. Conclusion. Representing knowledge in an uncertain domain is crucial for advanced artificial intelligence systems to make accurate decisions. Probabilistic models, fuzzy logic, machine learning, and hybrid approaches are used to handle uncertainty effectively. Ongoing researches and advancements will continue to improve the representation of uncertain knowledge in artificial intelligence systems.